Okay, so we've talked about 3 examples of network optimizations. Simple transport or transporting model, a simple assignment model where essentially you're transporting one and only one thing, and then a transshipment model where you have 2 phases of transport. Okay, the next couple models we're going to consider have to do with network models in which the flows have yields. That is, the amount that goes into one thing isn't always equal to the amount that comes out of one thing. Okay, it may be more, it may be less. So, for example, you can consider processes where there's waste. That is, if you're making something out of wood and you have to saw the wood, to make a table or a chair or something, there's some amount of waste. That is, the amount of wood that goes into that process isn't necessarily the amount that comes out in the table, because you've sawed away some or you've cut away some or something. So there's been a waste or a reduction in the amount of something. Okay, or you can consider something where there's addition. So the amount that goes in is less than the amount that comes out. So more comes out than you put in, such as something that involves interest, like a bank account. If I invest money, the amount of money I put in should be less than the money that comes out. I want the money that comes back out of the investment to be more than I put in, right? Otherwise, I wouldn't invest in it. So those are some general examples of real-world processes where yields happen. Okay, so let's consider, for our first example, a paper company who specializes in recycling. So they take in paper products of 3 different forms. They recycle it to produce paper products of 3 different forms. Okay, the problem is the amount they take in is more than the amount they can put out. That is, the recycling process wastes or has to use up or get rid of part of the product. Okay, so if I took 10 sheets of paper in and I recycled them, I may only get 8 sheets of paper out of that process. So 2 of them were lost to waste or some other factor. So here's just a table to kind of help us describe this situation. So the 3 kinds of paper that can come in are given by 3 rows. So there's just sort of normal white paper, notebook paper, printer paper, whatever. Mixed paper of different colors and different, maybe different gloss types or whatever, and then newsprint, so newspaper. Okay, so those are 3 kinds of paper this company can take in, and they can turn that into 3 different kinds of paper output they can sell. Okay, office paper, catalog paper, and napkins. Okay, the inputs, the 3 inputs have a supply. That is, there's only so much of it we can get. Right, there's only so much of it we can buy to turn through our recycling process into the outputs. And the outputs are a percentage of what goes in. So if I used white paper, if I had 100 sheets of white paper, I could recycle that into office paper, but I'd only get 85 sheets out. From 100 in, I only get 85 out. So the 85% comes out, which means 15% was lost, wasted, and so forth. It turns out you can't even produce office paper from newsprint, which is why there's a little dash here. So that's not even possible because of the recycling process we use. Okay, and newsprint, being sort of a cheaper paper, yields no office. You can't yield office paper, and it yields a lower percent of catalog and napkins than the other 2 kinds. So there's kind of like good paper, medium paper, and kind of cheap paper. We can recycle each of those for a certain loss in product into 3 different kinds. And obviously, the better the paper, the more you can get out of the process. Okay. Now, there's a profit we can make for each ton that we make. So if we use 1 ton of white paper, we'd get 85% of a ton in office paper. Or we could choose to turn it into 90% of a ton of catalog paper, or 95% ton of napkins. But which one we choose to turn it into will be dependent on how much profit we can make. Okay, and there's a demand for each. I'm going to treat the demand as a maximum. Okay, so we may want to take in, right, all 300 tons and 600 tons of white and mixed paper, turn them into office paper, right, because that's the most profitable, but we can only sell a certain amount of office paper. Right? There's only so much demand. So the supplies are a maximum, likewise the demands are a maximum. Okay, and we're going to maximize as our objective profit, so we're going to use whatever supply we can, subject to meeting but not exceeding demand, to maximize profit. Okay, so I'm going to copy these into Excel. We'll talk about how to do it. Okay, let's see here. Make that clear. So this was office, this was catalog, and this was napkins. All right. Now, I'm going to represent this in a diagram again to make it somewhat clear what's going on. It'll also help us understand, okay, the yield constraints a little better. Okay, so we have three kinds of paper that come in: white paper, mixed, and newsprint. Okay, there's a process that will yield, okay, office paper. Okay, if the white paper that comes into that, okay, will yield out only 85% of what goes in. Okay, so if one goes in, 0.85 will come out. Okay, so this is white paper converted to office paper. We can convert mixed paper, okay, to office paper, but for every one that goes in, you only get 60% out, 0.6, right? And so forth. So you can represent all of these things this way, okay? So just using a diagram, I'm just trying to illustrate. Now, you can't use newsprint to make any office paper, okay? So then we would consider the three different ways we could make catalog paper and the three ways we could make napkin paper, right? By representing these sorts of yields, okay? Now, this diagram might help sort of understand, okay? However, when it comes to the model in Excel, instead of using this tabular form like we have for other network models, I'm going to convert this to a different form, a different look to it, okay? Specifically, what I'm going to do, okay, is break everything down into, instead of a table of 3 rows and 3 columns, one of which is not an option, I'm just going to use all 8 of these possibilities as 8 columns, okay? So I have, say, white paper converted to office. I have white paper can be converted to catalog. White paper can be converted to napkins. Okay, mixed paper can also be converted to office. Mixed paper can be converted to catalog. Mixed paper can be converted to napkins. Newsprint can only be converted to catalog and napkins. Okay, so just shorthand to represent the 8 different processes we can go through. Okay, those are going to be my decision variables. That is, I'm going to decide how many tons of the input I want to put into the process for making that particular output. Okay, so there's only 8 options I have, not 9, because I can't use one of the inputs as a way to get one of the outputs. Sorry about that. Scroll that back. So those are going to be my decision variables. Okay, so again, I'm going to put them all in a single row as opposed to a tabular form. Okay. Now, objective. We still want to use some product. Since this is a linear model and we find that one so useful, we're going to sum product, right, these things. Okay. Except we don't want to sum product the amounts that go into the process, we want to compute the amount that comes out. Does that make sense? So first we have to calculate output. Okay, so the white to office paper yields 85% of what you put in, and so forth. White to catalog yields 90%. White to napkins yields 95. And you have 0.6, 0.7, 0.8, and then finally 0.65 and 0.6. Okay. So I can now compute the amount I put into each process multiplied by the yield of that process gives me the amount that would come out. Okay. So for example, if I put 100 tons of white paper into making office paper, I'd get 85 tons out. If I put 50 tons of white paper into making catalog paper, I'd get 45 tons out, and so forth. Okay. Now I know how much profit I get from office paper. Okay, $25. So whether that office paper was made from white or that office paper was made from mixed, however many tons I get of it, I can sell all of them for $25 each. I can sell catalog paper for $20, and I can sell newsprint or napkins for $18 a ton. So now I can use sum product to multiply my output amounts by the profitability, or the profit amount, for how much I can sell each of that for. Okay, which means I can compute how much profit I'd make. All right, make those numbers. Shrink some of these down so we can see it. So just given these two inputs that I've made up here, we would make a profit of $3,025. Okay, so that's our objective. So now we can talk about our constraints as well. Okay, and our constraints say, well, there is limits on supply of papers. Okay, so whatever I use white paper for, okay, so all the columns that involve white paper, if I multiply those by 1, sum them up, okay, so sum product decision variables, okay, and make that absolute multiplied by this row, is how many tons of white paper I'm choosing to use. So far I'm using 100 for this process, 50 for this process, 0 for this one, meaning I'm using 150 tons of white paper. That's got to be less than or equal to my capacity of 300 tons. All right. There we go. So this is white paper supply. We can do mixed paper supply. Label these so we can see them easier. So the use of mixed paper summed up is constrained to be less than or equal to 600 tons. And the use of newsprint, right, two different uses we have for it, we're going to constrain that to be less than or equal to 400 available tons. Okay, that's what we have so far. So we've taken care of that part of the model. I'm going to erase it. Taking care of this part of the model, computing our objectives. We've taken care of the yields, computing outputs. Okay, so the only other constraint we need to consider is the demand. So we have office paper demand. So whether we're getting office paper from white paper or mixed paper, we want to sum the product of the outputs, not the decisions, but the outputs, by this row. Oops. And constrain that to be less than or equal to the demand. We have catalog demand. So there's 3 ways you can get catalog paper. Regardless of all the ways you get it, right? We want to constrain that we don't make any more than 750 tons and napkins. So 3 ways you can make napkins. However much we make from all 3 of those ways will be constrained to be less than 550.
Those are based on outputs, right?
And those are, yes, so these final 3 constraints are based on the calculated outputs, which are the inputs multiplied by their yield. Okay? Yeah. So we have our decision variables. We had to do some intermediate calculation to figure out how much output we get, since it's not equal to the input. We have our objective function, and we have constraints, some of which are on the inputs, the decision variables, some of which are on the outputs computed from the decision variables. Okay? So, we could have done this in that tabular form. It would have looked a little funny, especially since one of the cells shouldn't have been computed and so forth. It turns out this model is a little bit easier for this and other kinds of problems where you have yields. So we know our decision variables, we know the objective that we want to maximize, and we know the 6 constraints that we have to be less than or equal to their constrained value. Okay. And as always, we need to constrain that the decision variables don't become negative. Otherwise, right, we might choose to yield negative things. I don't know that we would, but we might try to yield negative or use negative amounts of things so that we can sort of use negative mixed paper for catalog, so we can use more for office and still not violate supply. Okay. So let's run the model. So 176 point something tons of white paper is used to make office paper, such that it yields 150 tons of office paper, okay, because it's at 85% yield, and so forth. 123 tons of white paper for catalog. We don't use white paper to make any napkins, right? We don't use mixed paper to make anything but napkins. And we use newsprint to make catalog paper, not napkins, okay, for a maximum optimal profit of $19,000 plus. Okay. Now, which constraint, it does make sense in this case to ask which constraints are binding. Now, we've only chosen to use 4 decision variables. The other 4 we chose not to use. We chose not to put anything into that part of the process. So which constraints were binding? Well, as you would probably expect, it doesn't make sense not to use all your supply, because the more you make, the more you sell, the more profitable you are, right? So the 3 supply constraints are binding, and the office paper demand is binding. That is, we made all the office paper that we could possibly sell, okay? Then we use the remaining supply of white paper, and then mixed and newsprint, to make as much catalog and napkins that we could, not necessarily not to meet demand, but up to the supply we had of them. If that makes sense. Okay. Yes. Question.
So for the, if we were talking about binding constraints, we wouldn't really discuss, I guess, the zero factor.
Yeah. So the question is that implicit constraint that things can't be negative. Technically, that's binding, I guess, because we chose to use exactly 0 of something. Generally, we don't call that out, just because that implicit constraint, it doesn't help us understand the problem to understand that binding constraint, because it's a limit on sensibility. It doesn't make sense to do anything less than 0. Right? So it doesn't aid our understanding. I wouldn't expect you to call it out. If you do, it's not wrong. Right? That is a binding constraint by definition. In this case, that binding constraint bound 4 of our decision variables. The other 4 decision variables that we chose non-zero values for were bound by the 3 supply constraints and 1 of the demand constraints. Yeah. So again, kind of going back in linear optimization, your number of decision variables is generally the number of binding constraints you will have, right? Because obviously if you aren't hitting a limit, you should try to do more, right? Increase or decrease decision variables, whether you're trying to maximize or minimize something. So technically 4 binding constraints for the 4 non-zero decision variables. The other 4 zero decision variables were bound by the same constraint 4 times over, right? The non-zero, or can't be non-zero, or can't be negative, constraint. So 8 decision variables, 8 technically binding constraints in that case. Yep. Maximal profit given. We could ask through optimization sensitivity, maybe how profitable would one thing have to be before we would change the optimal pattern. We could say how much better of a yield would we have to get from one process before we change the pattern. We could say how much demand could we have for office paper before that's no longer binding and we make something else, or so forth, right? We could change any one of the parameters to the model, use optimization sensitivity to say how much does that parameter need to change before the optimal solution changes, before a different decision becomes optimal. Okay, so that's a network yield with a network model, network optimization model with a yield. So input not necessarily equal to output in any particular flow, in this case of an incoming source of paper to the outgoing product we make from it. Question?
Sorry, I just have one more question.
Yeah.
On this one, on the previous models we did, we used kind of a matrix, and on this one we used just a kind of a...
Yeah, so the question...
Sorry. I guess is there kind of rules of thumb on when you would try to model it? Or
sure. Yeah, so the question is, in previous network models we used a table or a matrix, rows and columns, and in this one we did not. Generally speaking, I mean, my rule of thumb is usually the network models with yields, it turns out generally to be a little bit easier to do it this way, and it's instead of a matrix, just one long row. Particularly because depending on what source and which destination, or what source and what output you're choosing to do, the yield is different. Okay, that's not to say you can't do that in a matrix form. It just looks different in that case. What you would end up with is a matrix for your decision variables, a matrix for these yields, a matrix for the outputs, and then your constraints would either constrain rows or columns of that matrix, sometimes in different ways. And so we could have done it that way, certainly. Once you start getting into yields, especially in another problem we'll get to next, I think this model, or this way of laying it out, makes more sense. It's easier to read. Yeah. Okay, so let's talk about that next model. So that was a network optimization with a yield. There are other kinds of network optimizations with yields that really don't lend themselves to that matrix tabular structure because there's not symmetry in number of rows and columns and things. So in the last problem, if we go back and look at it, go back and look at it, this table was mostly filled in. There was one cell that wasn't, but this table was mostly filled in. Some network optimization models, you have lots of sources, lots of destinations, but very few of the combinations make sense. Okay, so you end up basically with a table with lots of holes in it, or lots of values that you can't select from. In this case, there was one cell that you couldn't select to make office paper from newsprint, but every other combination you could choose to do. Some network optimization models will have much sparser of a table to fill out, in which case the tabular matrix form really doesn't make sense. It just too many holes, too many things you have to think about constraining or not allowing to be decision variables. In this case, you could have made this table and you would have just had to make sure that this bottom left cell wasn't a decision variable. That is, you didn't let the model choose to do that. If there were a lot more holes, you'd have a lot more picking and choosing of decision variables. So particularly, we're going to look at an example now where that's the case. So this is a fairly complicated description. We're going to illustrate it on the board behind me to help make sense out of it. Then we're going to turn it into an Excel model in that row form. So not a row and column tabular form, but just one long row. Okay. So we have an oil refinery. This oil refinery takes in crude oil, raw oil you get sort of out of the ground. Okay. And it's going to, in the end, produce 4 kinds of product, 4 things we can sell. Okay. But there's a process you go through to make those products from the input. So one source, 4 outputs, 1 input, 4 outputs. But the process to get from the input to each of the outputs looks different for each one. Okay, so now you can kind of see where there's not going to be a tabular form where the same rules apply to each row or each column. Different rules apply to different ones. All right, so here's the rules. The crude oil comes in. It first goes to what we call a distillation tower, distills the oil. If you put 5 barrels of oil in, you get 3 barrels of distillate, one kind of intermediate product out, and 2 barrels of something called just low-end byproduct. So there's the distillate process just sort of separates sort of the good parts of the crude oil from the bad parts. Okay, you get 3 barrels of good part for every 5 barrels you come in. You get 2 barrels of bad output from every 5 that come in. Okay, so we'll illustrate that real quick. So we have something called our tower, okay, where the crude oil comes in. Okay, if 5 barrels come in, 2 barrels come out as low-end byproduct, and 3 barrels come out as distillate. Okay, that's all that says. The low-end byproduct we can sell. That's something we just sell as is. There's nothing more we want to do to it. It's just the worst part of the crude oil. Right? So we separate it out and then just sell it for something cheap. The distillate, so what the other part that comes out, the better part we use to make something else out of. So the distillate is used to make gasoline and as input, what we call feedstock, into another part of the process. Okay? So I'm not going to put a bubble here just yet. I'm just going to leave that and say we can either use this to make gasoline or we can use some of it to go to another process, something called catalytic cracking. So something called the cracker. Okay. The catalytic cracking requires, so if 2.5 barrels come in, for every 2.5 barrels of distillate you send to the cracker, you get out 1.6 barrels of something called catalytic gasoline, okay, and 1 barrel of something called high-end byproduct. So again, this cracker kind of separates or takes this gas incoming distillate from the crude oil and sort of splits it into 2 different forms. The key is, if you'll notice, we get more out than we put in. So the cracking process actually uses water in the real world, but the cracking process actually can produce more output than you put in, but the ratio of how much of each kind of output is fixed. That is, for every 2.5 barrels that come in, you always get 1.6 out of catalytic gasoline and 1 out of high-end byproduct. The high-end byproduct will sell. Okay, so that's our second product we sell. So you can see you can make low-end byproduct, just one part of the process. With 2 parts to the process, you make high-end byproduct. Okay, You sell that. Now, this distillate that came out of the tower, you can mix with your catalytic gasoline. To either make premium gasoline or regular gasoline, both of which we can sell. So that's the last two products we sell. Now, to make premium gasoline, you need 75% catalytic and 25% distillate. So you're just going to blend the two together at a ratio of 3 to 1 to make premium gasoline. So if I put 3 barrels of catalytic gasoline in, 1 barrel of distillate, that's the 3 to 1 ratio, I'd get 4 barrels of premium gasoline. Right? So no yield there. As much as you put in, you get out, but you have to put in a certain ratio. Regular gasoline is made from a cheaper ratio. That is less of this good stuff, more of this sort of basic stuff. Okay? So this is a model meant to help us understand the process. I'm going to put that up white on the board for the video. So crude oil comes in. For every 5 barrels that comes in, it goes through this tower that separates out the good parts from the bad parts. You get 3 parts of good for every 5 in, 2 parts of bad. The bad stuff, called low-end byproduct, you sell. Okay? You don't do anything else with it. The good part, called distillate, okay, you can either use to blend making gasoline, or you can send it to a catalytic cracking process, which produces high-end byproduct that you sell, or catalytic gasoline, which is what you use to blend to make premium and regular gasoline. So we have crude oil coming in. We're going to figure out, if all that comes in, how much makes this, sell it. How much makes this, and then we have some decisions to make. Okay? How much of that distillate do we want to pass down this path? How much do we want to go over here? What comes down through this path makes some things. However much it makes through this process, or how much you get out of this process, you can decide based on how much distillate you chose to keep, not send through the cracker, but keep by itself, blend it with certain ratios, sorry, to make 2 more products you can sell. Okay. Now, I'll use a different color to kind of represent this. Where can we make decisions in this process? Well, we can make a decision here about how much crude oil we want to use. Okay. Probably we'll have some supply that we're limited to. We don't get to decide how much comes out of the tower process. We choose how much goes in. The process determines how much comes out. Okay? But we do get to decide for one of those outputs how much we use for one part of the process, how much goes on to another. Okay? How much we use through here determines how much comes out here. But then we get to choose how much of this versus how much regular distillate do we want to blend making premium gasoline. How much do we want to use to blend making regular, right? So how much catalytic gas, if you had 100 barrels of catalytic gasoline and plenty of distillate, would you want to use that to make more premium gasoline or more regular? Because you use less of it to make more regular, right, to sell. You'd have to use more of it to blend with your distillate to make premium. Okay? So we're going to be given, so those are really the 4 decisions we can make. Everything else in here is kind of determined by the process. So we're going to have to put all this into a model representing the yields of things. We're curious, we're interested in the low-end byproduct, the high-end byproduct, and the premium and regular gasoline that we can make, because those are the 4 things we can sell. That's the outputs of the process, the end outputs of processes that we sell. All right. So that's all that was trying to say. I probably won't give you a homework assignment nearly this complex, okay? But it's good to understand how to do it. From this description on the screen, you'd want to draw a picture to help understand what's going on, okay? That at least helps me. So here's the final keys to the project, or keys to the problem. The tower has a capacity, okay, of 50,000 barrels. That is, you can't send more than 50,000 barrels into it. Okay. The cracker has a capacity of 20,000 barrels. Presumably, this is over the course of a day or a month or something. That's the limit of how much it can do. There's demand for gasoline. Okay, so we can't make more gasoline than is sellable. That is, there's only so many gas stations to sell to. So there's a demand or a limit on the amount of gasoline we should make, because there's a limit to what we can sell. Crude oil has a cost. The tower has a cost operating it. The cracker has a cost to operate it. So the more you put through the process, the more costs, electricity, whatever it is to run them, to make that. And then finally, there's revenue or profit you can make from the low-end, high-end byproducts, regular and premium gasolines. Okay, so this didn't come in a nice form I can copy and paste, so we're just going to have to try to remember some of this. Let's go make an Excel model. Now, the easiest way to make a model in Excel for something like this is to take the picture you've drawn or thought of drawing, okay, and basically just represent every part of the process, because everything has to be either calculated or decided. Some things we get to decide how much to put through. Some things are calculated, and it's just however much we put in, we know how much or calculate how much comes out, right? We don't get to choose how much comes out. So let's start with what the first thing we can do, which is how much comes into the tower. So this is how much crude oil we're going to give to the tower. So the tower produces two things. It produces distillate and low-end byproduct. Okay, we don't get to choose those things. That's just determined by how much we put into the tower, right? For the distillate, we can choose how much goes into the cracker, so the input into the cracker, and then we can choose how much we use to blend to make gasolines. Okay, I'll put that in just a second. For the cracker, right, we choose how much goes in, but we calculate how much comes out. And what comes out is either high-end byproduct or something called catalytic gasoline. Okay. So then we can choose trying to think how to word this, how to put this in. We can choose how much distillate is used to make regular gasoline. We can choose how much distillate is used to make premium gasoline. Okay. And we can choose how much catalytic gasoline is used to make regular gasoline and how much catalytic gasoline is used to make premium gasoline. Okay. All right. So those are some things we can do or choose or figure out. Okay. So tower input, that's a decision variable. I'm going to make it look as such. And I don't know, let's assume we'll do something like initially 10,000 barrels. Okay. Now, what comes out as distillate is governed by, right, the process, which says 3 out of every 5 barrels of tower input becomes distillate, or 60%, right? So we can just compute 60% of the tower input. Okay. This makes as much sense as anything else. I'm just going to do it this way. So if I put 10,000 barrels in, I'd get 6,000 barrels of distillate. I'd get 0.4% or 4,000 barrels in low-end byproduct. Okay. Okay with that so far? All right. how much distillate goes into the cracker. Okay, that's a decision variable. So if I have 6,000 barrels of distillate, I don't know, let's put half of it in the cracker to start with, see what that does. Okay, the cracker is computed. How much comes out as high-end byproduct? It's 1 barrel for every 2.5 barrels in, okay, which is like 2 barrels for every 5, or 40%. Okay, so 40% of what comes in to the cracker comes out as high-end byproduct. Okay. How much comes out as gasoline? I can't do that one in my head. We'll just say 1.6 divided by 2.5 times the input, right? So the ratio, we get 1.6 in for every 2.5 out. So whatever that ratio is, multiplied by the input is how many barrels we get out, right? So 1,920 barrels out of the cracker as catalytic gasoline. Okay. Now we get to decide the rest of everything. That is, how much we use of distillate and catalytic gas to blend into making regular and premium gasoline. Okay. All right. So those are our decisions. Now, decisions and calculations. I've blended them all together. Okay. We do need to figure out what our objective is. Our objective is to maximize profit. Well, how do we get profit? Well, we get some amount of profit for every low-end byproduct, something like $36. We get so much profit from our high-end product, something like what was it, 44. Okay. Now, we get so much profit for how much regular gasoline we make, but we need to compute how much that is. That is, if we put, I don't know, if we put 1,000 barrels of of distillate to make regular gasoline, we're constrained. We would have to use 1,000 barrels of catalytic gasoline because it's a 50-50 blend. But we'd get the sum of that, that is 2,000 barrels of regular gasoline made out of that, right? Okay. Is that okay with everybody? Okay. I just want to make sure that's clear. So, if I multiply $50 by both of those, that's how much profit we'd get, right? Because you get 1,000 barrels of regular gasoline plus another 1,000 because of you mixing two things together. Okay, so each of them multiplied by 50. Right. Just want to make sure we're okay with that. And then finally, what was the other? Premium is $55. Okay, so this is revenue that comes in. Okay, so all I have to do here, I'm kind of running off the screen, is use sum product to multiply each of these things up here by each of these things down here. Okay, so only some of them get multiplied by something, but that tells us how much money we bring in. Okay. We also have costs. Okay. We have to pay for the crude oil, right? The crude oil costs $28 a barrel, but not only do we have to pay for the crude oil, we have to pay for every barrel we send through the tower, right? So $28 plus $5, $33 of cost for every barrel of crude oil that goes into the tower. You have to both buy it and pay the cost of running the tower. Okay? So that's one cost. The other cost is operating the cracker. Okay? So the cracker costs $6 per barrel that goes into it. So of the incoming, what we send into the cracker, we have to pay $6. Okay. So same as before. I make these absolute. Copy this down. Oops. So in this case, we have less revenue than we do profit. Okay. Mainly because I didn't use everything. Let's try using everything up here. So maybe let's use 500 of that and 1500 of that. There we go. That looks a little better. So now at least we're making more profit or more revenue than we have in cost. Our profit is just, sorry, not sum, revenue minus cost. So with these particular decisions, I'd make $58,000. Okay. Make each of these a currency. So now I've captured pretty much my decision variables, calculations necessary, and my objective. I still have to consider my constraints. Okay. And what are my constraints? Well, I'm going to use my standard pattern of sum products here. I'm going to constrain the number of barrels we send into the tower. So 1 times that. I'm going to constrain that, right, to be less than the tower capacity. So I'm going to make this formula use all the row or all the columns, so I can just copy the formula down each time. But in this case, this value must be less than or equal to 50,000. Okay. Maybe make a few of these shorter to read. We can get it all to fit on one screen eventually. We're close. Let's go for it. Close enough anyway. Oh, here we go. Just name this distilled. All right. So that's the first constraint. 50,000 barrels possible to send through the tower. The next constraint is the cracker capacity, so it can only handle 20,000 barrels. And the last constraint will be the gasoline demand of 16,000. So cracker capacity, anything that comes into the cracker here, so obviously that's just 3,000. That has to be less than or equal to 20,000. And the number of barrels of gasoline we make, whether that's premium or regular. Okay, so 1 times all of those must be less than or equal to 16,000. Okay, there we go. So those are my constraints. So I've represented my decision variables, what I can decide in the process. I've calculated the other parts, right? I've represented my objective. I've represented constraints. Okay. Now there's actually 2 more constraints, right? We didn't consider yet. The first is, sorry, the ratios. Yeah. So however many distillate barrels I use to make regular gasoline has to equal the number of catalytic barrels I use to make regular gasoline. So if you think about the ratio thing again, what you would end up with is, right, one has to equal the other, right? Which means if you add one and subtract the other, right, it has to equal 0. So you could just use 1 and -1 in either order, okay, to say this value must be, must be equal to 0. I'm just not doing it right. There we go. Now, for making premium gasoline, you need to use 3 barrels for every 1 of distillate for every 1 barrel of catalytic gasoline. Okay, so if I multiplied, no, I'm sorry, I get that backwards. If I multiplied the distillate barrels used by 1, okay, I'd need more, no, I had that right. I need more catalytic barrels, right? So multiply catalytic barrels by -1, distill it by 3, those should sum to 0. Okay? So for every 3 barrels of distillate, I need 1 catalytic. So to make those come out, right, to be that ratio, add 1, subtract the other, must be equal to 0. Okay. All right. Well, let's put it in. Decision variable, decision variable, decision variable. Okay. Here is my objective. I want to maximize. I have 3 constraints which must be less than or equal to a certain value. I have 2 constraints which must be strictly equal to a certain value. Okay. So that's what the model looks like. Now, there's many ways you can do this. Okay. You could have done this with a matrix. It would have looked bad, but you could have done it with a matrix. You could have made 2 of these last 4 decision variables calculated instead of decisions, because if you decide how many distillate barrels to use to make regular, then that automatically determines how many catalytic barrels you need, right? So, I mean, you could have calculated that as opposed to decide it, okay, and so forth. Now, there's actually some more constraints, right? What constraints have we missed? Not quite as obvious, right?
Have to do our 0, like greater than
1. Oh, okay. The implicit that you can't choose to do 0 things. Yeah, I don't think we'll need that in here. We'll talk about that one in a second. There's actually some other constraints we missed first. For example, what keeps me from deciding to use more, let's say, catalytic gasoline to blend than catalytic gasoline I made, right? So for every barrel of catalytic gasoline I make, okay, I can't use more than that to blend into gasoline, right? So I need to make sure that that part of the process, right, sums to 0. Right? You can't use more than you made of that stuff, which it looks like right now I am. Actually, I'm using less than I made, which is probably just a bad decision. Okay. Similarly, the amount of distillate you make, okay, you have to choose to use, right? You either use it into the cracker or you use it as part of your blends of gasolines. Right? So again, you need what comes out of the tower as distillate to equal what you use to go into the 3 other parts of the process that use distillate. Okay? So 1 times the 1, -1 times the rest. Right? Make sure that all of these 3 values sum to something that equals this value. All right. Hopefully I don't have to convince you too much, but if you had done this with a matrix, in addition to it being kind of sparse and having certain cells that don't make sense, it also starts to become hard to calculate stuff like that, where these parts of the process have to sum to this part of the process, where it's not a whole row equaling a whole column anymore because there's holes in the table or holes in the matrix, right? This way, it kind of at least makes a little more sense that you say, well, whatever this value is has to equal, right, this value, which means one value minus the rest has to sum to 0. All right, I'm going to name my constraints just so we know. So this is tower capacity. This was cracker capacity. This was gas demand. This was regular gas blending. This was premium gas blending. This was, I guess, the catalytic gas use. Right? You can't use more than you make. And this was distillate use. Okay. So making sure that we only use what we make. All right. So those constraints there, we'll add those last two. So those values must be equal to their zeros as well. And now we can talk about, do we need to implicitly limit anything to being non-negative? I don't believe we're going to need to do that, and here's why. We'll try it and see, but I don't think it would ever make sense to use negative of anything to produce negative outputs, right? If you're trying to maximize your sum, plus you're limited to everything summing to zero, that is, what goes out or what comes out has to have gone in, plus whatever yield it may have calculated. Okay, so let's try it and see. So we'll solve. Okay. So it did find a solution, which is good. Looks like I'm going to have to expand some columns to see the numbers. That's all right. All right, so what did it decide? Well, it found the maximum profit is $408,800. We did not use the entire tower capacity, right? So we only purchased 38,666 barrels of crude oil, which made a certain amount, right? Distillate and low-end byproduct. Of the distillate, we passed most of that through the cracker. Okay. Oh, I'm sorry. We did find negatives. So missed it when I looked. So in fact, it found we could negatively blend regular gasoline, right, for a loss, but offset that by making more premium gasoline. So I was wrong. We have to assume non-negative. There we go. All right, better answer. 37,000 barrels of crude oil, okay, making 22,000 barrels of distillate. Again, most of that still goes into the cracker, okay? And what we found was it's not worth blending any of the distillate and catalytic gasoline into regular gasoline, right? That doesn't make as much money, okay? Now, that makes sense in the sense that it's not just that it made less money, but for the cost of making the extra catalytic gasoline necessary for the cost making the extra catalytic gasoline necessary to blend to premium gas, to make premium gas, we make a good enough profit from it that we want to use all of the catalytic gasoline to make premium. Okay, even though we could have used less of it to make regular gasoline doesn't give us enough profit to make that worthwhile to do. Okay, that's all that means. So we could use optimization sensitivity to ask the question, how profitable would regular gas have to be before we'd start producing it? Right now we produce 0 gallons or barrels of regular gasoline. How profitable would it need to be to make it so? Let's ask that. Before we do, let's ask, what's the binding constraints? Well, we know the tower capacity is not binding. We know the cracker capacity is not binding. Right? We're not using the capacity of those two things. We are bound by the gasoline demand. So we're making as many barrels of gasoline as we can make. We're just making it all as premium gas, not regular. Okay. Now, these constraints, right, always would have been binding because they had to be equal. Just saying inputs have to equal outputs. Don't be concerned, this value here, just the rounding error that came out, it ended up with something negative, but very, very close to 0. So 10 times, or something times 10 to the negative 12. That's 0, right? It just rounding wise, the numerics came out. This didn't exactly equal 0. It's close enough that we ignore it. Okay, So these 4 constraints had to be binding. Of these 3 constraints, only 1 was binding. Okay. Okay. All right. So let's do the optimization sensitivity now and say how profitable would regular gasoline need to be before we'd make it. So I'm just going to use this cell here. We'll say optimization parameter. We'll start at 50 where we are now. Let's go up to 60. I doubt we'll need to go that high, but we'll find out. And these 2 cells need to equal that one. Now this is a case where I had to put the optimization parameter in a different cell because I needed to refer to it in 2 places, the way the model was set up. And if I put 2 parameters in 2 places, that's 2 parameters, not 1. So we'll do our optimization parameter analysis report. Our variable is in, this is not sheet 2, we're on sheet 7. Our variable is in H5. We'll go ahead and take, oops, all of our decision variables and the objective in the output, and we'll do 11 points. So for each gasoline blend from 50 to 60 in increments of 1, how profitable does regular gas have to be before the optimization optimal parameter or optimal solution changes? Somewhere between $55 and $56, right? And once regular gas can be sold for $56, more than premium, right? Then we choose to make it not premium. Right? So we chose, instead of making 0 gallons of regular gas, to suddenly make 0 gallons of premium gas, because now it's just the more profitable thing to do. Easy enough. Now, obviously, as the price of regular gas goes up from 50 to 55, our optimal solution doesn't, or optimal objective doesn't change, right? We don't make any more money because we're not making gas at that point, regular gas. So the regular gas price goes up, our objective value stays the same because we're not making that. Once we hit 56, the higher it goes, the more profit we can make. Because now we've chosen to make gasoline, regular gas, not premium. Okay. That's a network optimization with a yield. The hardest part is going to be taking that word description and making a diagram so that you understand all the points that you'll have to decide and all the points you'll have to calculate. Once you've done that, just translate them into cells. I would do it in a single row here in the Excel sheet to make your model. The reason why doing that makes sense is because then you can use some product like we have here to compute your objective and constraints. And the key is each row of your constraints and even your objective only use some of the rows right from the model. Only certain things like decision variables, only certain computed values, right? And no row of the constraints uses the same values, right? Most of these values are empty or 0. That's all I'm saying. Which is why a matrix would look maybe a little funny. But this way, at least you can label each constraint clearly. You can see what parts of the model affect that constraint. And through highlighting cells, you can see which ones are decision variables that you can decide on versus ones that are hard or calculated and they are what they are. You don't get to choose. Okay. All right. We'll do one more example, close for the night. So that covers network optimization, where you have flow from sources to destinations, or flow through processes, where you have inputs and outputs. Another different kind of linear optimization we'll call integer optimization is where you force all the decision variables to be whole numbers, integers. For example, if you think back to the last week or last lecture problem we did with the furniture, making chairs, tables, and desks. Technically, we found an optimal solution that said something like make 3/4 of a desk, right? 166.6 desks or something. That doesn't make sense, right? You can only make whole numbers. Linear optimization or integer optimization would allow you to constrain the decision variables to be integers. In Excel, that's literally what you do. You create a constraint that says these decision variables must be integers. Just put it in that way. In that example of the furniture, all it would have done probably is just round down, because rounding up would have violated a constraint. So probably not going to do anything unexpected. There are some kinds of problems where only integers possibly make sense, and there might be a trade-off between you can't just round down one and round up another, right? You'd have to pick between true integers, okay? That's just a constraint that you add to say make these integers. I'm not going to do an example of that tonight. Instead, what I'll do is an example of a more constrained form, which is binary decision variables, where the decisions are 0 or 1. So it's either yes or no, true or false, but two things you can decide. That's just a special constraint. That's just another special constraint. Instead of saying any whole number, you're saying just these two whole numbers, 0 and 1. Okay, so let's do an example of that. Okay, so that's what we're saying here. So let's say a company has some a research and development department, and they have 5 projects that research and development can look into doing. Okay, each one has a net present value, which is sort of how much money that could make us by researching and selling, or researching and producing whatever that project involves. But it costs money up front to pay the people to do research and development on. So we also have a budget that limits how many projects we can undertake. So we want to maximize that net present value without violating the budget. So we can't do all 5 projects. We want to figure out which subset to do, subject to our budget. The binary part, obviously, is that you can't half do a project or do a project 2 times. You can either not do it or do it once. Right? So it's binary. It's on or off. It's do it or not do it. Okay. So here's the parameters. So net present value and the expense that it takes for these 5 projects. We want to maximize the net present value of the chosen projects, subject to the expense of the chosen projects being less than 160. Okay. Simple enough. So I'm just going to make decision variables out of this one row, and just to start with, we'll just choose to do projects 1 and 2, not projects 3, 4, and 5. So my decisions are 0 and 1. Do it or not. The nice thing is that works nicely with SumProduct, because I can multiply the 0s and 1s by their net present value, and all it does is sum up the 1s, right? The net present value of the projects we chose. And likewise, for the expense, if I just sum the projects by their expenses, it only sums up the ones I chose, those expenditures, not the ones I didn't choose, and that's the thing I want to limit. So this is our objective. We want to maximize net present value of the chosen projects, subject to the expenses being less than the budget, and we want to know which ones get chosen. So these 5 are our decision variables. This is our objective to maximize. This value is constrained. The expenses are constrained to be less than or equal to the budget. And finally, we need to tell the model that the decision variables are constrained to be binary. So that's just another type of constraint. So here you can see there's a variable type or bound. We can say these highlighted decision variables are bound to be binary. if you wanted to do integer optimization, there's an option for integer, right? So literally the difference, right, in terms of putting it in Excel is clicking one button or the other. Okay. So in this case, they're binary. So given that, now we don't have to tell it they have to be non-negative or anything anymore, because now they're constrained to be 0 or 1, nothing else. If you look on the Model tab, you'll even see that. Sort of you have to scroll down a little bit, but it even says cells B2 through F2 must be binary, okay, in addition to being our decision variables. So now we can solve. So the optimal solution was to do projects 1, 3, and 4, not 2 and 5, for the best net present value there, and for exactly meeting the budget. Okay. Now it turns out there happened to be a sum of projects whose expenditures exactly equaled the budget. It wouldn't always come out that way, right? Because you have to either do it all or do it not at all. You're not necessarily guaranteed that your budget constraint will be equal, okay, even though it would still be binding. Okay, so this is kind of a special case. Now that we're constraining things to be binary, it means that a binding constraint need not actually equal its limit. Okay, that is, there might have been, and I'll show you an example in a second, a selection of projects whose expenditures were less than 160, but no other project could be selected to keep it under 160. That is, selecting any additional project would be over budget. So the budget constrained us from selecting one more project. Really, we were constrained because we couldn't half do a project, right? We could have equaled the budget by half doing one more project, but we were constrained to either do it all or not at all. So the budget and the binary constraint kind of influence one another. Both could be considered binding. Okay. All right. That's pretty simple, right? Binary optimization, just like any other linear optimization, except your decision variables are limited to being 0 or 1. Okay. However, came slightly off the screen. There are some special classes of constraints that we can think about having given binary optimization or binary decision variables. So one might be a constraint that says I need at least one of, let's say, projects 2 and 5 to be selected. That is, there's something about projects 2 and 5 that we've promised we will do at least one of them, maybe both. Okay, obviously that we didn't do that now, so that's a new constraint. So let's do this. So this is going to be an at least one constraint. And literally what we can do is if we multiply by 1, oops, not 3, project 2 and 5, those decision variables. So again, let's do sum product. These things multiplied by these. Okay. We want to constrain that that's greater than or equal to 1. That is, we just want to say you have to have at least selected 1 or 5. 2 is selecting both 2 and 5, sorry, would be okay, but you had to at least do one of them. Okay, so obviously right now we're doing 0 of them, which would violate this constraint. So let's add that as a constraint. That value must be greater than or equal to 1, and recompute. So before we got a net present value of 34. Now that we've added a constraint, the best net present value by selecting projects we can get is 32, because we forced it to do at least project 2 or project 5. It chose to do project 5, 4, and 1. And of course now you can see the budget doesn't actually, or the expenses don't equal the budget. But obviously we can't do project 3, that would put us over budget. We can't do project 2, that would put us over budget. So the budget is binding selecting one more project. In addition, we're bound by selecting project 2 or 5. We only chose to do one of them, which was the minimum amount we could have chosen to do. That would be a binding constraint too. Okay. The budget is binding only because they're binary decisions again. So whether you say it's the binary decisions that are binding or the budget that's binding, you can make a case for both. It's the interplay or the interrelation of the two. So that's one new kind of constraint that we can think of having when you're talking about binary decisions, is you have to select at least one or at least two of this subset of projects or this subset of things. Yeah, question?
What if you want to change it so that you had to do one or the other?
That is an excellent question. In fact, we would call that a mutually exclusive kind of constraint. So let's talk about that. Let's imagine you can't do projects 4 and 5 together. That is, whatever there is about those two projects, they require some of the same resource, of which you only have one. So you have to do one or the other, but not both. Okay? So that would be mutual exclusion kind of constraint. How would we represent that? Well, if you took one project and added the negative of the other, you'd want that to be exactly 0. Oops. To say that you can't have both, right? So having, I'm sorry, this would not be 0, right? So another way you could do that, so you could do one minus the other, constrain that can't be 0. You don't have a good way to input that in Excel or an analytic solver platform. The better way to do that would be to say, if I don't want both of those, then the sum must be less than or equal to 1. Right? So in this case, I want no more than one of these two. They're mutually exclusive. You can't have both. You can have neither, or one but not the other, but not both. Okay, so like the at least one constraint, you sum things up. They must be greater than or equal to the minimum you want. If you want at least one, you have to have at least one. Mutual exclusion says you sum them up. They have to be less than or equal to the max you want to do between them. Right? So if I want only one of those two, or you could say I only want 2 of these 3, any of that would work.
So I was thinking about an exclusive OR. So in that case, would we need 2 constraints here where we'd say that it can't, so it has to be less than.
Okay. So you want one, exactly one.
Right. So
one but not the other. Can't do neither, can't do both.
So
You could do that the same, just constrain this to be strictly equal to 1. Yeah.
Okay.
That would be exclusive OR, saying you have to do one of them but not both of them. Yeah. So mutual exclusion mutual exclusion just means one without the other. Right? And doing neither fulfills that technically. So let's make that a constraint. So I'll add that. So that must be less than 1. It's obviously not. So let's re-optimize. And now instead of a $32,000 or $1 million net present value, whatever this is, we have 31. We've selected to do project 2 and 5. So we had to do at least one of 2 and 5. We couldn't do both 4 and 5. Okay. So now what we've ended up choosing to do is 2 and 5. Okay. Let's see. One more kind of constraint. Contingency constraints say, if you do one project, or if you want to do a certain project, you have to do another one. Okay. So let's just do as an example. If you want to do project 2, okay, you have to do project 1. Okay, so that would be a contingency constraint. Okay. So if you do 2, you have to do 1, meaning you can do 1 without 2, or you could do neither. Okay, but if you do 2, you have to do 1. Okay, so just to help you understand how you think about this, it's easiest to write these things out sort of in a table sometimes. So you can do neither, that's legal. You can do 1 without 2, that's legal. Okay. You can not do 2 without 1. That's illegal. Or you can do both. Okay. So, looking at these possibilities, how could we write a greater than or equal to constraint that would assure that we don't ever do this combination, but we do any of the other 3? That was a hard question. All right, I'll give you a hint. The value you select for P1 is going to have to be greater than or equal to something. P2. That's all these conditions say, is P1 can't be less than P2. That is, we require P1 be greater than or equal to P2. That is, you can choose the same values for them, they're equal, or you can choose a value bigger for P1 than P2. That is, do P1, not P2. The only thing you can't do is P2 without P1. Right? So P1 must be greater than or equal to P2. If you're going to write this for some product, you would say P1 minus P2 must be greater than or equal to 0. Okay. That's just algebraically manipulating that. Right? All right. So if I multiply P1 by 1, P2 by -1, some product, those two coefficients, that must be greater than or equal to 0. Right? So the way we have it now, we're doing P2 without P1, which means this sum product down here becomes negative, which we don't allow. It has to be greater than or equal to 0. So let's add that as a constraint. And resolve. So, given we have to do at least one of project 2 and 5, we can't do 4 and 5 together. And if we do project 2, we have to do project 1. And of course, we have a budget. The optimal solution is to do projects 3 and 5. So that meets the first constraint. We did project 5. It meets the second constraint. We didn't do project 4. And it meets the third constraint. We just decided not to do 2 at all. Okay. So we still could have done 1, but it wasn't optimal to do that. It was better to do 3. So we ended up doing projects 3 and 5 for an optimal net present value of 30 in this case. Again, we're not using all the budget, but there's no product or no project we could have still done that would keep us under budget. Okay. Well, project 4 you could still do and be under budget, but we can't do 4 and 5, so that constraint was obviously binding on us as well. Oh yeah, you're right. It would be. Sorry, I was looking at the 8 instead of 30. You're right. You can't do project 4 and still be under budget. I've been doing 3 and 5. You're right. So there's no project we could do, still stay under budget, and obviously still meet these 3 constraints. Now, I gave these special names. They're special names only in the sense that they describe a relationship. You have to have at least one of these, or at least n of these numbers, of these selected. Mutual exclusion, you can't have more than one of these, right? Or more than n of these. Contingency is the trickiest one. It just means if you choose one, you have to have the other, which just means 1 times 1 minus 1 times the other must be greater than or equal to 0. Okay. So the easiest way to think about it is to draw out a little table, figure out what the relationship really looks like in an inequality form. So in this case, P1 must be greater than P2. The value we select for P1 decision must be greater than P2, which really means P1 minus P2 must be greater than or equal to 0. Okay, that made it easy to put into the Excel spreadsheet in the sum product sort of standard form that we have. Okay, that takes care of binary optimization. The only thing we didn't get to is another special kind of constraint known as a linking constraint. So we won't bother talking about that. We're out of time tonight. Next week, we will stop talking about optimization. So we're done with optimization. We'll talk about something called simulation, which is how you handle when you have uncertainty. That is, you don't know what value a particular parameter has. You only know a distribution of values that it could come from, you know, a minimum and a maximum or something like that. So when you don't have an idea of exact values to use in your model, you have to use a technique known as simulation with the model to actually make any decisions or determinations. Okay. So that's what we'll cover next week. Assignment 5, I will post to Blackboard by tomorrow morning. It'll cover network and integer optimization, or network and binary optimization. It might have some of those special constraints like contingencies or mutual exclusion or something. The network model may or may not have yields. Okay, you have the examples we did tonight. Hopefully those are enough. If not, you can refer to the book. It has ample more examples than I was able to cover to learn how to do those. So, sorry I was over by a bit. Have a good week, and I'll